This video is audio content only. It does not contain any video footage or images. If you are expecting visual content, please be aware. This is intentionally provided in an audio-only format. We recommend listening to the audio rather than watching the screen. Thank you for your understanding. Welcome to today's exploration of one of Africa's most enigmatic aquatic mammals. Have you ever heard of the Potamogalidae? If not, you're about to discover a remarkable family of creatures that bridge the gap between land and water in extraordinary ways. These elusive animals, known as otter shrews, have inhabited African waterways for millions of years, yet remain largely unknown to most of the world. In this narration, we'll dive into their unique adaptations, mysterious behaviors, and the threatened habitats they call home. Prepare to meet some of nature's most unusual survivors. Chapter 1. Ancient Divergence and African Origins. The story of otter shrew evolution is one of ancient continental connections and long separation, revealing surprising relationships that remained hidden until modern molecular techniques illuminated their true family tree. When researchers first encountered these peculiar creatures in the rivers of Central Africa, their streamlined bodies and aquatic lifestyle suggested kinship with otters, while their long snouts and small size evoked comparisons to shrews. Yet neither impression captures their actual evolutionary heritage, which traces back tens of millions of years to a time when Africa's fauna was taking shape in isolation from the rest of the world. The most remarkable finding in otter shrew evolutionary biology concerns their relationship with an entirely different group of mammals living on an island hundreds of miles away. Molecular genetic studies have conclusively demonstrated that the closest living relatives of African otter shrews are the tenrecs of Madagascar, those diverse and peculiar insectivores that occupy ecological niches ranging from hedgehog-like spiny forms to nearly naked burrowing species. This connection between mainland African otter shrews and Malagasy tenrecs represents one of the most significant biogeographic relationships within African mammal evolution, speaking to a shared ancestry that predates the distinctive adaptations both groups would later develop. The separation between these two lineages occurred during the Eocene epoch, a pivotal period in mammalian evolution when many modern orders were establishing themselves across the globe. Based on comprehensive molecular clock analyses calibrated with fossil constraints, scientists estimate that otter shrews and tenrecs diverged approximately 47 to 53 million years ago. More refined estimates place this split at around 47.5 million years before present, with confidence intervals extending from roughly 40 to 56 million years. This time frame situates the divergence in the middle to late Eocene, an era characterized by warm global temperatures and extensive tropical forests that would have provided ideal habitat for small insectivorous mammals. Understanding why this split occurred requires examining the geological context of that ancient world. Madagascar had already separated from the African continent by this time, having rifted away during the breakup of the supercontinent Gondwana much earlier, around 165 million years ago. However, the evolutionary split between otter shrews and tenrecs occurred far more recently than Madagascar's geological separation, indicating that the ancestral population reached Madagascar through later dispersal events rather than vicariance. The island's isolation created an evolutionary laboratory where tenrecs would diversify into an extraordinary array of forms, exploiting ecological opportunities in the absence of competition from other mammal groups. Meanwhile, the ancestors of otter shrews remained on mainland Africa, where they would face different selective pressures and eventually develop their specialized semi-aquatic lifestyle. The depth of this evolutionary divergence becomes apparent when examining phylogenetic trees constructed from genetic data. These trees consistently show exceptionally long branch lengths separating otter shrews from tenrecs, indicating substantial genetic differences that accumulated over millions of years of independent evolution. The long terminal branches leading to both modern otter shrew species further suggest deep divergences and extended periods of separate evolutionary trajectories, even within the otter shrew lineage itself. Such patterns tell us that we are looking at the remnants of what was likely once a more diverse radiation of these mammals, with most intermediate forms having gone extinct, leaving only a few highly specialized survivors. The recognition of otter shrews as distinct from tenrecs at the family level represents a relatively recent development in mammalian taxonomy. For much of scientific history, otter shrews were classified as a subfamily within Tenrexidae, grouped together with their Malagasy cousins based on shared primitive characteristics. This arrangement reflected the understanding that both groups represented ancient lineages of African origin, but it did not fully appreciate the magnitude of time and evolutionary change separating them. The elevation of Potamogalidae to full family status came in 2016, based on comprehensive phylogenetic analyses that incorporated multiple genetic markers and complete taxonomic sampling of both groups. This taxonomic revision was not merely an academic exercise in splitting hairs. The decision to recognize otter shrews as a distinct family rested on both the temporal depth of their separation from tenrecs and the accumulation of unique morphological and anatomical features that distinguish them. While otter shrews and tenrecs share certain ancestral characteristics that reveal their common origin, they have diverged substantially in their skeletal structure, dental patterns, and soft tissue anatomy. The absence of a clavicle or collarbone in otter shrews, for instance, sets them apart from tenrecs and represents an adaptation to their swimming lifestyle. Their highly modified foot structure, with fused second and third toes forming a grooming comb, differs from the foot anatomy seen in most tenrecs. Placing otter shrews within the broader context of African mammal evolution requires understanding their position within Afrocyracida, an order that encompasses several families of small, primarily insectivorous mammals. Alongside the otter shrew family Potamogalidae and the tenrec family Tenrecidae, this order includes the golden moles of southern Africa in the family Chrysochloridae. Together, these three families form a natural group, united by molecular evidence and certain shared anatomical features, though their external appearances vary dramatically due to their different ecological specializations. The relationships among these Afrocyricidan families have been extensively studied using modern molecular techniques. Genetic analyses consistently recover golden moles as having diverged first from the common ancestor, with otter shrews and tenrecs forming a sister group relationship within the suborder Tenrecomorpha. This arrangement places the split between golden moles and the Tenrecomorph lineage at approximately 58 to 68 million years ago, during the late Paleocene or early Eocene. The subsequent divergence between otter shrews and tenrecs occurred roughly 10 million years later, as mentioned earlier. One particularly interesting aspect of Afrocyricidan phylogeny concerns the difficulty researchers have encountered in resolving certain deep relationships. While the sister group relationship between otter shrews and tenrecs is well supported, the connection between this Tenrecomorph clade and golden moles shows less statistical confidence in some analyses. This uncertainty likely reflects the extreme antiquity of these divergences and the accumulation of so many genetic changes over time that the original phylogenetic signal has become obscured. Such challenges are common when attempting to reconstruct relationships among lineages that separated more than 50 million years ago. The Afrocyricids themselves represent just one branch of a much larger evolutionary assemblage known as Afrotheria, a superorder of mammals that originated and diversified primarily in Africa. This remarkable group includes not only the small insectivorous forms like otter shrews, but also some of the largest land mammals on Earth. Elephants and their extinct relatives belong to Afrotheria, as do the aquatic sirenians, or sea cows, the rock-dwelling hyraxes that resemble large guinea pigs, the trunk-snouted elephant shrews with their long legs adapted for bounding across African savannas, and the bizarre aardvark with its powerful digging claws and long sticky tongue for harvesting termites. The discovery of Afrotheria as a natural evolutionary group ranks among the most significant findings to emerge from molecular systematics. Before DNA sequencing techniques became available, anatomists had struggled to understand the relationships among these morphologically disparate mammals. Elephants seemed obviously related to other large herbivores, while the small insectivorous forms appeared to belong with shrews and moles, and sea cows were thought closest to other aquatic mammals. Yet molecular data revealed that all these creatures share a common ancestor that lived in Africa during the age of dinosaurs or shortly after their extinction, making them more closely related to each other than to any mammals from other continents. Within this Afrotherian radiation, the Afrosauricidans represent the lineage that retained the most ancestral characteristics in terms of body size and dietary habits. While their relatives evolved into multi-ton herbivores or specialized termite eaters, the ancestors of otter shrews, tenrecs, and golden moles maintained a lifestyle focused on consuming invertebrates and small vertebrates. This dietary conservatism should not be mistaken for evolutionary stagnation, however. Each of these families developed remarkable specializations for exploiting particular microhabitats. Golden moles became fossorial specialists, essentially filling the ecological role of true moles in southern African ecosystems. Tenrecs diversified into an array of forms on Madagascar, from spiny hedgehog-like species to nearly hairless burrowing forms. Otter shrews, as we shall explore in subsequent chapters, became aquatic predators with unique swimming adaptations. The fossil record of otter shrews, while limited, provides tantalizing glimpses into the early history of this lineage. Specimens assigned to the family Potamogalidae have been recovered from Eocene deposits in southern Africa, extending back approximately 40 million years. These ancient representatives confirm that the otter shrew lineage has indeed been present in Africa since very early in its evolutionary history. A particularly notable fossil find from Pliocene deposits in southern Spain represents the first and only evidence of the family occurring outside Africa. This extinct genus Potamogalidae suggests that otter shrews once had a broader geographic distribution, possibly extending their range during periods of favorable climate and habitat connectivity between Africa and southern Europe. The molecular clock estimates that place the origin of the otter shrew family itself at around 59 million years ago, in the Paleocene or early Eocene, suggest an even longer history than the fossil record currently documents. This apparent gap between molecular estimates and fossil evidence reflects the challenges of paleontological sampling, particularly for small mammals which are less likely to fossilize and be discovered than larger species. The early Paleogene environments of Africa remain poorly sampled by paleontologists, so it is likely that future discoveries will push back the known fossil record of otter shrews closer to the molecular estimates of their origin. Examining the genetic architecture underlying otter shrew evolution reveals the molecular mechanisms that have shaped their divergence from tenrecs. Studies examining nuclear genes, including ADRA2B, AR, GHR, and VWF, alongside complete mitochondrial genomes, have provided robust support for the monophyly of Potamogalidae, meaning that all otter shrew species share a common ancestor exclusive to their lineage. These analyses have examined genes involved in diverse cellular functions, including hormone receptors, growth factors, and blood clotting proteins, ensuring that the phylogenetic signal does not depend on any single genomic region that might give misleading results due to unusual evolutionary pressures or horizontal transfer events. The statistical support for key nodes in the otter shrew phylogenetic tree is generally very strong. Bayesian posterior probabilities, which represent the confidence in particular evolutionary relationships, exceed 95% for most critical branches, including the monophyly of the family and its sister relationship with Tenricidae. This robust support gives researchers confidence that the evolutionary history they have reconstructed accurately reflects the true pattern of descent. Such confidence is important because taxonomic decisions like elevating Potamogalidae to family status rest on the reliability of these phylogenetic inferences. Anatomical evidence complements the molecular data in supporting the distinctiveness of otter shrews within Afrosauricida. The tarsal bones of the ankle region show characteristic configurations that unite all otter shrews while distinguishing them from tenrecs, providing shared derived characters that diagnose the family. These anatomical features evolved in the common ancestor of all otter shrews and have been inherited by all living species, providing independent corroboration of what the molecular data indicate. The evolutionary position of otter shrews within Afrotheria illuminates broader patterns in the early diversification of African mammals. The split between the primarily herbivorous panungulate lineage, leading to elephants, hyraxes, and sea cows, and the Afro-insectivilian lineage, encompassing Afrosaurocidans, elephant shrews, and aardvarks, occurred around 80 to 90 million years ago in the late Cretaceous. Africa was then an island continent, separated from other landmasses by ancient oceans, creating conditions for in situ evolutionary radiations of endemic mammal groups. The Afrosaurocidans represent one such radiation, descending from small insectivorous ancestors that survived the mass extinction event that ended the age of dinosaurs. Following their origin, Afrosaurocidans diversified into the three families we recognize today during a span of roughly 10 to 15 million years in the Paleocene and early Eocene. This rapid diversification produced distinct lineages adapted to different ecological niches. The subterranean golden moles, the diverse tenrecs eventually reaching Madagascar, and the semi-aquatic otter shrews. Each family then underwent its own subsequent diversification, though with strikingly different outcomes in terms of species diversity. While tenrecs proliferated into more than 30 living species on Madagascar, otter shrews remain represented by only 3 species, suggesting different evolutionary dynamics or different extinction pressures on the African mainland versus the island. Their evolutionary distinctiveness, representing nearly 50 million years of independent evolution, underscores their conservation significance, a topic explored in Chapter 6. Understanding the evolutionary journey of otter shrews from their shared ancestor with tenrecs to their present specialized form provides essential context for appreciating their biology. Their aquatic adaptations, hunting behaviors, and anatomical peculiarities all represent evolutionary solutions that emerged during their long, independent history on mainland Africa. The next chapters will explore these adaptations in detail, but recognizing their deep evolutionary roots helps us understand that we are observing the products of nearly 50 million years of natural selection, acting on a lineage that has witnessed the rise and fall of countless other mammalian groups. In the rivers of Central and Western Africa swim not merely interesting animals, but living representatives of one of Africa's most ancient mammalian lineages. Chapter 2. Built for Water. The transition from terrestrial to aquatic life represents one of the most demanding evolutionary challenges a mammal can face. Water is 800 times denser than air, creating resistance that penalizes inefficient body forms. Maintaining body temperature in an environment that conducts heat away from the body 25 times faster than air requires exceptional insulation. Hunting in murky water, where visibility extends only centimeters, demands alternative sensory strategies. The otter shrews have met these challenges through a suite of morphological adaptations that transform them from typical insectivorous mammals into specialized aquatic predators, while remaining distinct from the true otters whose ecological niche they superficially resemble. The most immediately striking feature of otter shrew anatomy is the streamlined body profile that reduces drag as they move through water. Unlike their terrestrial tenorec relatives with more cylindrical torsos, otter shrews possess elongated bodies that taper at both ends, creating a fusiform or torpedo-like shape. This configuration minimizes turbulence along the body surface during forward movement. The giant otter shrew exemplifies this adaptation most dramatically, with a head and body length reaching 30 to 35 centimeters, giving it a distinctly otter-like silhouette when viewed from the side. The body appears round in cross-section at the shoulders and midsection, then gradually narrows toward the hindquarters before flowing into the powerful tail. The pelage of otter shrews represents a masterpiece of mammalian fur engineering. Unlike aquatic mammals that rely on thick blubber layers for insulation, otter shrews maintain warmth through their remarkable coat structure. The fur consists of two distinct layers working in concert. A dense undercoat of fine, soft hairs creates a thick mat that traps air against the skin. These underhairs are so tightly packed that water cannot easily penetrate to the skin's surface. Overlying this insulating layer are longer, stiffer guard hairs with flattened tips that give the coat its characteristic glossy sheen. These guard hairs shed water efficiently, allowing the animal to emerge from the river already beginning to dry. The waterproofing properties of otter shrew fur are so effective that observers report the coat dries within minutes after the animal leaves the water. This rapid drying is essential because a mammal with wet fur faces severe thermoregulatory challenges. The air trapped in the undercoat provides insulation both in and out of water, maintaining a microclimate against the skin even during submersion. When an otter shrew dives, the compressed air in the fur creates millions of tiny bubbles that cling to the guard hairs, giving the animal a silvery appearance underwater. This air layer reduces direct water contact with the skin while providing buoyancy that must be overcome through active swimming effort. The coloration of the fur follows a pattern common among aquatic animals known as countershading. In the giant otter shrew and the Ruwenzori dwarf otter shrew, the dorsal surface is covered with rich dark brown fur, while the ventral surface transitions to white or yellowish tones. This arrangement provides camouflage from predators viewing the animal from above or below. When seen from above against the dark riverbed, the brown back blends into the substrate. From below, the pale belly becomes less visible against the bright surface light filtering down through the water. The chin, throat, and upper chest of the giant otter shrew are particularly white, creating a striking contrast visible when the animal surfaces to breathe. The Nimba dwarf otter shrew departs from this pattern, possessing uniformly dark fur across its entire body, which may help it blend into shadowy microhabitats among roots and vegetation along stream banks. The head of an otter shrew reveals numerous adaptations for underwater hunting. The muzzle is broad and distinctly flattened, quite unlike the pointed snouts of terrestrial shrews. This flattened profile reduces drag as the animal pushes its head through water while searching for prey. The end of the snout terminates in a leathery pad, typically heart-shaped and divided by a longitudinal groove. This pad lacks fur and houses the nostrils on either side. Critically, small muscular flaps conceal these nostrils completely when the animal dives, preventing water from entering the nasal passages. This valve system operates automatically during submersion, reopening when the otter shrew surfaces to breathe. The eyes of otter shrews are notably small relative to body size, reflecting a reduced reliance on vision for hunting in the often turbid waters of African forest streams. The external ears are similarly reduced, appearing as small, fur-covered projections that add minimal drag while swimming. These reduced sensory organs for vision and hearing are compensated by the remarkable development of the tactile sense, centered in the facial whiskers. The muzzle bears a dense array of long, stiff whiskers known as vibrissae, which serve as the primary hunting sensors for otter shrews. These are not ordinary hairs, but highly specialized mechanoreceptors, each one embedded in a follicle rich with nerve endings and blood sinuses that amplify tiny movements. Additional vibrissae extend from locations above the eyes and along the lower jaw, creating a sensory net that detects water movements with extraordinary sensitivity. When prey items like small fish or freshwater crabs move nearby, they create pressure waves and currents in the water. The vibrissae detect these disturbances, allowing the otter shrew to precisely locate prey even in complete darkness or heavily silted water where vision provides no useful information. The tail morphology varies significantly between species. The giant otter shrew possesses a laterally compressed tail measuring 24 to 29 centimeters, nearly as long as the head and body combined, creating a blade-like structure covered with short, dense fur. The Ruwenzori dwarf otter shrew has a tail with less dramatic lateral compression, appearing more rounded in cross-section, though still slightly flattened. The Nimba dwarf otter shrew has a tail that is essentially round in cross-section. The tail contains between 31 and 34 caudal vertebrae bearing neural spines, transverse processes, and hemal arches. The limbs of otter shrews are short and powerful, keeping the body mass concentrated near the center of the animal. All three species possess 5 digits on each foot, tipped with curved claws suitable for gripping slippery rocks and muddy banks. A distinctive feature found in all species is syndactyly, the fusion of the second and third toes on each hindfoot into a single functional unit. The presence of webbing between the toes varies by species. The Ruwenzori dwarf otter shrew possesses webbing between all digits of both forefeet and hindfeet. In contrast, the giant otter shrew and the Nimba dwarf otter shrew lack webbing entirely, though the giant otter shrew's feet have margins fringed with stiff hairs. The skeletal system reveals numerous adaptations that distinguish otter shrews from their terrestrial tenrec relatives. Perhaps most notable is the complete absence of a clavicle or collarbone, a feature that sets them apart from tenrecs and most other small mammals. The clavicle typically serves to maintain separation between the scapula and sternum, preventing the shoulder from collapsing inward. Its absence in otter shrews allows greater flexibility in the shoulder joint, permitting the forelimbs to be held tightly against the body during swimming to minimize drag. The scapula or shoulder blade is long and narrow in the giant otter shrew, lacking the pronounced acromion process that in other mammals serves as an attachment point for parts of the deltoid muscle used in powerful limb movements. The humerus or upper arm bone is notably elongated relative to the forearm bones, an unusual proportion among mammals. A prominent feature of the humerus is the large tubercle that projects upward like a claw. This tubercle blocks against the scapula during certain movements, limiting the range of motion at the shoulder and stabilizing the forelimb in a streamlined position against the body. The elbow joint shows design features emphasizing stability over mobility. The lower end of the humerus forms a broad rectangular joint surface that articulates with the forearm bones. The ulna possesses an exceptionally long olecranon, the projection that forms the point of the elbow, comprising approximately 19% of the total ulna length and providing substantial leverage for the triceps muscle. The overall elbow structure restricts sideways motion, essentially locking the forearm into a fore and aft plane of movement that prevents positions increasing drag during swimming. The bones of the wrist show reduction in number compared to typical mammals. Some carpal bones appear to have fused together, possibly the central bone with the scaphoid or the scaphoid with the lunate bone. This consolidation creates a more rigid structure, sacrificing fine manipulation ability in favor of structural stability. The metacarpal bones of the palm, in contrast to the fused carpals, are elongated, extending the overall length of the forelimb. The hind limb skeleton reveals adaptations for generating powerful movements despite the relatively short leg length. The femur or thigh bone is short relative to the size of the pelvis, which positions the hip socket in an upward orientation. This configuration increases the mechanical advantage of the leg muscles. A small third trochanter, a bump on the femur shaft where gluteal muscles attach, appears unusually far down the bone compared to its position in tenrecs, changing the leverage relationships for the powerful rump muscles. The tibia and fibula, the two bones of the lower leg, fuse together in their lower third, creating a rigid structure in the ankle region. Both bones are relatively straight, without the pronounced curvatures seen in many terrestrial mammals. The ankle bones themselves showed distinctive features that distinguish otter shrews from tenrecs. The malleoli, or ankle knobs, are long and narrow, restricting rotational movement of the foot. The talus bone has a sharply defined transition from the dome-shaped articular surface to the neck of the bone, again limiting rotation. The calcaneus, or heel bone, bears an extremely long calcaneal tuber, the heel projection where the Achilles tendon attaches, providing enhanced leverage for the calf muscles. The skull structure accommodates the broad, flattened muzzle while housing the specialized sensory apparatus. The overall skull shape appears narrow when viewed from above, widest at the brain case and tapering toward the elongated rostrum. In side view, the forehead line runs nearly straight without pronounced angles. The nasal passages are constructed to allow the nostril flaps to seal effectively during dives. The tear duct and associated opening that connects the eye to the nasal passage are absent, a modification apparently related to the reduction of the olfactory system. The skull base includes an ossified or bony auditory bulla, the chamber that houses the middle ear bones, providing protection for the delicate hearing apparatus during the pressures of diving and swimming. The zygomatic arch or cheekbone is incomplete, perhaps reducing weight while maintaining structural integrity where it matters most. Below this incomplete arch sits the glenoid fossa, the socket where the lower jaw articulates with the skull. The vertebral column consists of 7 cervical or neck vertebrae, 16 to 17 thoracic vertebrae bearing ribs, 5 to 6 lumbar vertebrae in the lower back, 5 sacral vertebrae fused into the pelvis, and the 31 to 34 caudal vertebrae of the tail. This vertebral formula provides both flexibility for lateral undulations and stability in the core body region. Internal anatomy shows modifications for the aquatic lifestyle as well. The digestive tract is relatively simple, with an oval stomach and intestines reaching 55 to 68 centimeters in total length, approximately 4 times the body length. Unlike many mammals, otter shrews lack a cecum, the blind pouch at the junction of small and large intestine that in herbivores houses symbiotic bacteria for digesting plant material. The absence of a cecum is consistent with an entirely carnivorous diet that requires less complex digestive processing. The pancreas shows a highly branched structure, increasing the surface area for producing digestive enzymes necessary for breaking down the protein-rich diet of fish, crustaceans, and aquatic invertebrates. The brain achieves volumes between 720 and 1270 milligrams in the dwarf species, and between 3720 and 4640 milligrams in the giant otter shrew, notably larger relative to body mass than in closely related tenrecs. Female reproductive anatomy includes a bicornuate or 2-horned uterus with an endotheliocorial placenta structure that differs from the epitheliochorial placenta found in tenrecs. Males have testes positioned in the pelvic region near the pubic bone, lying within fibrous skin pouches called cremaster sacs. Males possess a relatively long penis adapted for aquatic mating. Female otter shrews bear 4 pairs of nipples distributed along the abdomen, with 2 pairs in the pectoral region, 1 pair on the abdomen proper, and 1 pair in the inguinal region near the hind limbs. Males possess testes positioned in the pelvic region near the pubic bone, lying within fibrous skin pouches called cremaster sacs. Males possess a relatively long penis adapted for aquatic mating. Female otter shrews bear 4 pairs of nipples distributed along the abdomen, with 2 pairs in the pectoral region, 1 pair on the abdomen proper, and 1 pair in the inguinal region near the hind limbs. The size differences between the 3 species relate to their ecological specializations. The giant otter shrew weighs between 300 and 950 grams, with a total length including tail reaching 53 to 64 centimeters. The Ruwenzori dwarf otter shrew weighs 75 to 135 grams, with combined head, body, and tail lengths of 22 to 35 centimeters. The Nimba dwarf otter shrew weighs approximately 125 grams, with a body length of 15 to 22 centimeters, plus a tail comprising a quarter to a third of body length again. Together, these morphological adaptations, from the streamlined body and waterproof fur to the specialized sensory systems and modified skeleton, transform otter shrews into effective aquatic predators. Each feature addresses specific physical challenges of the freshwater environment while maintaining the basic mammalian body plan inherited from terrestrial ancestors. Chapter 3: Crocodilian Swimming in a Mammal Among. The thousands of mammal species inhabiting our planet, only one small group has independently evolved a swimming technique that reptiles perfected over 100 million years ago. When an otter shrew enters the water and begins to hunt, it propels itself forward through rapid side-to-side sweeps of its muscular tail, while holding its limbs tucked against its streamlined body. This crocodilian-style locomotion represents one of the most remarkable examples of convergent evolution between mammals and reptiles, arising from the similar hydrodynamic constraints imposed by moving efficiently through water. Most aquatic mammals employ very different swimming methods. Otters, despite their name's similarity to otter shrews, paddle with all four webbed feet or use dorsoventral tail movements, beating their tails up and down like the flukes of whales and dolphins. Beavers slap their flat tails against the water in powerful vertical strokes. Seals and sea lions employ their flippers in various paddling or underwater flying motions. Whales and dolphins undulate their entire bodies in vertical waves, culminating in the powerful up and down beats of their tail flukes. Among all these successful aquatic mammals, essentially none use the lateral tail undulation that characterizes both crocodilians and, uniquely among mammals, the otter shrews. The giant otter shrew demonstrates this swimming technique in its most refined form. As the animal pushes off from the muddy bank and enters a quiet pool in the forest stream, it extends its body into a straight line. The forelimbs press tightly against the sides of the thorax, minimizing any protrusion that would create drag. The hind limbs similarly fold against the body, their clawed toes pointing backward. A flap of skin along the inside of each hind foot allows them to be held snugly against the body, further reducing drag during swimming. In this streamlined configuration, the animal resembles a living torpedo, and all propulsive power comes from the tail. The swimming motion begins with a rapid lateral sweep of the posterior body and tail. The tail arcs to one side in a smooth curve, its flattened surface pushing against the water. As this curved shape moves through the water, it generates thrust through a complex interaction of pressure differentials and momentum transfer. The water resists being pushed aside by the broad face of the laterally compressed tail, and this resistance translates into forward motion for the animal. Before the tail reaches its maximum lateral excursion, the motion reverses. The tail sweeps back through center and continues to the opposite side, creating another power stroke. This alternating pattern of left and right sweeps generates continuous forward thrust. The frequency of these tail beats varies with the urgency of the moment. During leisurely exploration of a pool's edges, the sweeps occur at a measured pace, propelling the animal slowly forward while it probes among submerged roots and rocks with its sensitive whiskers. When prey is detected or danger threatens, the beat frequency increases dramatically. The tail becomes a blur of side-to-side motion, and the otter shrew accelerates with impressive speed for such a small mammal. The laterally compressed shape of the tail maximizes the surface area pushing against water during these power strokes while minimizing drag during the recovery phase of each sweep. This swimming technique creates a characteristic sinuous motion visible from above when an otter shrew swims near the surface. The body itself participates in the undulation, though less dramatically than the tail. A wave of lateral bending travels down the spine, originating in the lumbar region and increasing in amplitude as it proceeds posteriorly. By the time this wave reaches the base of the tail, the lateral displacement has become substantial, and the tail itself amplifies the motion further. The entire animal describes an S-shaped curve through the water, the curve shifting smoothly backward as thrust propels the body forward. Observing this motion in the giant otter shrew inevitably invites comparison with crocodilian swimming. A crocodile or alligator employs essentially the same technique, tucking its legs against its body and sweeping its powerful, laterally compressed tail from side to side. The similarity is not coincidental, but reflects the mechanical efficiency of this swimming method under certain conditions. For an animal with an elongated body and a muscular tail, lateral undulation provides excellent thrust while requiring relatively simple neuromuscular coordination compared to the complex paddling motions that demand precise limb timing. The otter shrew's convergence on this solution speaks to the power of natural selection to arrive at similar answers when faced with similar problems, regardless of the evolutionary starting point. The skeletal and muscular systems underlying this locomotion show clear specialization. The numerous caudal vertebrae of the tail provide both flexibility and strength. Each vertebra articulates with its neighbors through joints that permit lateral bending while restricting torsion that would waste muscular energy. The neural spines projecting upward from the vertebrae, the transverse processes extending sideways, and the hemal arches, downward curving bones found on the underside of the anterior tail vertebrae, all serve as attachment points for powerful muscles. The epaxial muscles running along the back of the spine and the hypaxial muscles along the belly contract in coordinated alternation. The left side muscles pull the tail leftward while the right side muscles relax. Then the pattern reverses. This coordinated contraction requires precise timing controlled by spinal pattern generators, neural circuits in the spinal cord that produce rhythmic motor patterns without requiring conscious input from the brain. The propulsive efficiency of this system is considerable. Unlike paddling, which generates thrust only during the power stroke of each limb cycle, lateral undulation produces relatively continuous thrust. As the tail sweeps through each half cycle, it pushes water backward and the reaction force pushes the animal forward. There are brief moments of reduced thrust as the tail changes direction, but proper phasing of the body undulation helps maintain momentum through these transitions. The result is smooth, sustained forward motion with minimal wasted energy. The hind limbs, despite being held against the body during routine swimming, can assist during specific maneuvers. When the giant otter shrew needs to make a sharp turn, a quick extension and sweep of one hind limb acts as a rudder, pivoting the body in the desired direction. During the final approach to captured prey, the hind limbs may splay slightly to act as brakes, allowing the animal to decelerate rapidly without overshooting. When swimming in extremely confined spaces where full tail sweeps are impossible, subtle movements of the hind limbs can provide auxiliary thrust. However, these represent supplementary functions rather than the primary propulsion mechanism. The Ruwenzori dwarf otter shrew employs a notably different swimming strategy that incorporates its webbed feet into the locomotion pattern. While this species retains the capacity for lateral tail undulation, it does not rely on this method exclusively. Instead, it combines undulatory movements with active paddling using all 4 feet. The webbing between the toes creates effective paddles that generate thrust when swept backward through power strokes. The 4 feet paddle in alternation with the hind feet, creating a quadrupedal swimming gait somewhat reminiscent of a dog's paddling motion, but integrated with the underlying body undulation inherited from the family's ancestral condition. This mixed locomotion strategy provides the Ruwenzori dwarf otter shrew with versatility. In open water, the combination of paddling and undulation generates substantial thrust for an animal of its size. In tight quarters among rocks and submerged vegetation, the independent control of 4 limbs allows precise maneuvering that would be difficult with tail propulsion alone. Each foot can adjust its power and timing independently, enabling the animal to rotate in place, hover at a particular depth, or execute complex 3-dimensional movements while tracking agile prey. The tail, though less dramatically compressed than in the giant otter shrew, still contributes to propulsion through its undulations and serves as a rudder for steering. The Nimba dwarf otter shrew represents what researchers interpret as the most primitive or least specialized swimming technique within the family. Lacking both the extremely compressed tail of the giant otter shrew and the extensive webbing of the Ruwenzori species, it must employ an intermediate strategy. The animal undulates its body and its more rounded tail while simultaneously paddling with its unwebbed feet. The paddling with unwebbed feet is less efficient than with webbed appendages, as much water slips between the toes during each stroke. Nevertheless, the paddling provides meaningful thrust and, importantly, gives the animal fine control over its trajectory and orientation underwater. This combination of undulation and paddling in the Nimba dwarf otter shrew offers insight into the evolutionary history of swimming in the family. The technique likely represents a stage similar to that employed by the common ancestor of all otter shrews before the lineage split into the three modern species. From this ancestral condition, using both undulation and paddling, the giant otter shrew lineage specialized toward extreme reliance on lateral tail undulation with corresponding tail compression and limb reduction in swimming function. The Ruwenzori lineage specialized toward enhanced paddling efficiency through the evolution of webbing while retaining substantial undulatory capacity. The Nimba lineage retained a more generalized approach that serves adequately in the small streams it inhabits, but lacks the performance extremes of its relatives. The duration and depth of dives vary with hunting strategy and habitat characteristics. Otter shrews are not deep divers compared to marine mammals. Their foraging takes place primarily at depths of less than 2 meters in forest streams and pools. Each dive typically lasts only a few seconds, just long enough for the animal to investigate a promising crevice or pursue a detected prey item. The brevity of these dives reflect several factors. The small body size of otter shrews limits their oxygen storage capacity in blood and tissues, constraining how long they can remain submerged. The energetic cost of maintaining body temperature in cold water creates time pressure to return to the surface. Most importantly, the prey they pursue, insects, small crustaceans, and tiny fish, occur primarily in shallow water among the substrate and vegetation where extended deep diving would serve no purpose. The transition from underwater swimming to surfacing involves a characteristic behavior pattern. As the otter shrew concludes a dive, it angles upward and accelerates with rapid tail beats. The animal breaks the surface nose first, the water streaming from its glossy guard hairs. It takes several quick breaths, the nostril flaps opening automatically to admit air. Within seconds, the animal may dive again or, if moving between hunting locations, continue swimming at the surface with just the top of its head and back visible above the waterline. Surface swimming employs a similar undulatory pattern to subsurface swimming, but adjusted for the different mechanical environment, where part of the body is in air rather than supported by water. After completing a foraging session, the otter shrew hauls itself onto the bank. Here, the limitations of its aquatic specializations become apparent. On land, the animal walks plantigrade, placing the entire sole of each foot flat on the ground from heel to toe with each step. This provides stable support, but results in a rather awkward waddling gait. The short legs must take rapid steps to move the elongated body forward. The heavy tail drags along the ground, leaving a characteristic sinuous groove in mud or sand that betrays the animal's passage. The otter shrew can move quickly on land when necessary, breaking into a bounding gallop where the hind limbs provide thrust while the forelimbs reach forward to brace each landing. However, such terrestrial speed comes at high energy cost and cannot be sustained. The animal is clearly out of its element, as ungainly on land as it is graceful in water. Upon reaching the safety of vegetation or a burrow entrance, the otter shrew engages in extensive grooming. This is where the syndactylous toe structure, that curious fusion of the second and third toes on each hindfoot, demonstrates its specialized function. The animal draws these fused digits through its fur repeatedly, combing through the dense undercoat to remove debris, parasites, and excess water. The two toes, united along their length but retaining their claws, form an effective grooming tool with fine spacing between the claw tips. This grooming implement reaches areas the animal's teeth cannot easily access and processes the fur more efficiently than would be possible with individual toes. The grooming ritual is not mere fastidiousness, but essential maintenance of the waterproof fur coat that enables aquatic life. Any matting or fouling of the undercoat compromises its insulating properties. Debris lodged in the fur prevents the proper arrangement of guard hairs and undercoat that traps air during swimming. Parasites like ticks or mites that attach to the skin can cause irritation and infection. The syndactylous grooming comb addresses all these issues, allowing the animal to maintain its pelage in optimal condition. The otter shrew typically spends several minutes grooming after each extended time in the water, systematically working through all areas of the body it can reach. During these grooming sessions, the otter shrew frequently assumes a sitting posture, balancing on its hind quarters with the tail providing additional support. In this position, the animal can bring one hind foot up to groom the head and neck, drawing the syndactylous comb through the facial fur and behind the ears. The forefeet, though not specialized for grooming, help spread saliva through the fur on the chest and belly. The tongue, though not as long and flexible as in some grooming specialists, contributes by licking the forelimbs, which then wipe over the face. After grooming concludes, the animal's coat shows the characteristic glossy sheen that indicates proper fur structure, and the otter shrew is ready to enter the water again with full waterproofing restored. The swimming locomotion of otter shrews thus represents a suite of adaptations that function as an integrated system. The lateral tail undulation that characterizes the family reaches its extreme development in the giant otter shrew, whose compressed tail and streamlined body create a remarkably efficient swimming machine that operates through purely crocodilian mechanics. The Ruwenzori species demonstrates that this ancestral undulatory capacity can be supplemented with paddling when webbed feet evolve to make such paddling efficient. The Nimba species shows that a less specialized intermediate approach remains viable in appropriate habitats. The syndactylous toe structure, though not directly involved in propulsion, enables the essential grooming that maintains the waterproof fur coat upon which all their aquatic activities depend. Together, these features transform otter shrews from typical terrestrial insectivores into specialized aquatic predators capable of exploiting a resource base unavailable to their land-bound relatives. Chapter 4. Hunting by Touch. The hunting prowess of otter shrews unfolds in an environment where most mammalian predators would be helpless. The forest streams of Central Africa, especially during the rainy season, run thick with suspended sediments that scatter light and reduce visibility to mere centimeters. Even in the dry season, when the water clears somewhat, the dense canopy overhead blocks moonlight and starlight, plunging the underwater world into near total darkness during the nocturnal hours when otter shrews actively hunt. In this lightless realm where vision provides little useful information, these small carnivores have perfected an alternative hunting strategy that allows them to detect, track, and capture agile prey with remarkable efficiency. Using their highly sensitive facial vibrissae, described in Chapter 2, otter shrews hunt primarily by touch and scent in calm pools and slow-flowing reaches. As the animal swims slowly through a pool with its muzzle extended, the vibrissae trail through the water ahead of and beside the face. When a small fish swims past, even at a distance of several centimeters, it creates pressure waves and subtle water currents that spread outward. These disturbances in the water flow bend the vibrissae in specific patterns, allowing the otter shrew to determine not only that something is moving nearby, but also the direction, distance, and approximate size of the disturbance source. This whisker-based detection system responds to real-time disturbances with minimal delay, providing actionable information for an ambush predator that must react in fractions of a second to successfully capture agile aquatic prey. The system functions identically in complete darkness as in dim light, giving otter shrews a decisive advantage over prey species that rely primarily on vision. In the darkness, these visual predators and prey species operate at a disadvantage, their reactions slowed by reduced sensory information. The otter shrew, meanwhile, hunts with unimpaired efficiency regardless of illumination. The actual hunting behavior begins when an otter shrew enters the water and swims to a favored hunting location. Upon reaching a promising pool with overhanging roots and submerged rocks, the animal slows its swimming and adopts a hunting posture. The body maintains a slight downward angle, keeping the muzzle near the substrate where many prey items hide. The tail continues subtle undulations to maintain position against gentle current, but the animal's attention focuses forward and sideways, processing the constant stream of tactile information from the vibrissae. For minutes at a time, the otter shrew may patrol slowly back and forth across a pool, systematically investigating likely prey refuges. The whiskers probe into crevices between rocks, sweep along submerged logs feeling for the characteristic vibrations of insect larvae, and trail through dense mats of aquatic vegetation where small fish might lurk. Each dive lasts only seconds before the animal must surface to breathe, so the hunting pattern consists of rapid dives alternating with surface breathing intervals. The otter shrew dives to check a particular crevice or root tangle, surfaces to breathe, then dives again to investigate the next promising location a meter or two away. When the vibrissae detect something promising, perhaps the faint water movement created by a crab's gill currents or the muscle contractions of a hiding fish, the hunting sequence accelerates dramatically. The strike itself happens with startling speed. The otter shrew's tail beats rapidly, accelerating the animal toward the detected prey location. The mouth opens, revealing the complete dentition of 40 teeth, arranged in the formula 3.1.3.3/3.1.3.3, with robust incisors and molars particularly adapted for crushing hard-shelled prey like crabs. If the prey is a fish, the otter shrew attempts to clamp its jaws around the body before the fish can accelerate away. The teeth sink in, and the otter shrew performs a rapid head shake that stuns or kills the prey through the combined effects of puncture wounds and violent whiplash. With prey secured, the animal kicks for the surface or the nearest bank. Prey is consumed on the bank rather than in the water, as the otter shrew needs stable footing to process its catch effectively. This bank consumption behavior serves multiple purposes beyond simple convenience. It reduces the risk of losing the prey to a struggle underwater, allows the animal to breathe freely while eating, and provides stable positioning for the considerable jaw force required to crush crab shells or tear apart larger fish. Capturing crabs demands particularly sophisticated tactics due to the formidable defenses these crustaceans possess. A freshwater crab of the size otter shrews commonly hunt, perhaps 4 to 6 centimeters across the carapace, wields powerful claws capable of delivering painful pinches. The chele can grip with surprising strength, and the hard exoskeleton resists casual bites. Observations reveal sophisticated problem-solving behavior that suggests these animals learn through experience which approaches succeed and which result in painful lessons. The preferred crab hunting technique involves approaching from behind or above to avoid the reach of the outstretched claws. When an otter shrew detects a crab through whisker sensation, it maneuvers carefully until achieving a favorable angle of attack. The initial strike targets the rear of the carapace or the junction between carapace and abdomen. Once the otter shrew has gripped the crab, it often uses its forefeet to pin the crustacean against the substrate or against its own chest. This immobilization prevents the crab from effectively deploying its claws. In a maneuver that appears almost intelligent in its deliberateness, the otter shrew then flips the crab onto its back, exposing the softer ventral surface where the legs attach to the body. Bites directed at this vulnerable underside can crack the thinner exoskeleton and reach the vital organs, quickly dispatching the crab. The robust molars prove essential for this crushing work. After the initial kill, the otter shrew must break through the hardened carapace to access the nutritious flesh within. The molars apply focused pressure to crack shell segments, which are then discarded or swallowed depending on their size and thickness. This processing occurs methodically on the bank, the otter shrew working through its catch piece by piece. Not all crabs can be safely attacked, however. Otter shrews show clear size discrimination, typically avoiding crabs larger than 7 centimeters across. These larger individuals possess chelae powerful enough to seriously injure an otter shrew, potentially crushing a toe or tearing facial tissue. The risk simply does not justify the reward when smaller, more manageable crabs are available. This size selectivity suggests that otter shrews can assess prey dimensions using their whiskers, perhaps by detecting the full extent of a crab's body as whiskers brush along its edges, or by recognizing the characteristic water displacement patterns created by crabs of different sizes. Individual dietary preferences add another layer of complexity to otter shrew hunting behavior. While all three species are carnivorous and all consume similar suites of prey when available, specific individuals develop distinct preferences that shape their hunting tactics. Some giant otter shrews become crab specialists, spending most of their foraging time investigating rocky areas and submerged root tangles where crabs shelter during daylight. Captive observations document that such individuals may consume 15 to 20 crabs in a single night when hunting is productive, a figure likely representative of wild foraging success for crab specialists. Other individuals develop preferences for fish, focusing their attention on pools and quiet eddies where small fish congregate. Frogs represent another significant prey category, though they appear to be less preferred than crabs or fish for reasons that are not entirely clear. When an otter shrew does capture a frog, the consumption method follows a stereotyped pattern. On the bank, the frog is oriented head first, and the otter shrew begins consuming it from the front, working its way backward through the body. This orientation may help avoid struggles from the powerful hind legs, or it may simply represent an instinctive consumption pattern inherited from ancestral insectivores that ate many elongated prey items and developed standardized handling techniques. Fish captured by otter shrews receive different treatment depending on their size. Small fish, those perhaps 2 or 3 centimeters in length, can be consumed whole in a few quick bites once brought to the bank. Larger fish must be processed before consumption. The otter shrew uses its teeth to grip the fish at various points along the body, and then performs pulling motions that tear the prey into manageable sections. This dismemberment requires the stable footing that bank consumption provides, as the otter shrew needs to generate considerable force. The separate chunks of fish are then eaten in succession, the otter shrew working through its catch methodically before returning to the water to hunt again. Beyond crabs, fish, and frogs, the otter shrew diet encompasses a remarkable diversity of aquatic invertebrates. Aquatic insect larvae, including those of dragonflies, stoneflies, and caddisflies, provide protein-rich morsels easily captured among the substrate. The detection and capture of these smaller prey items relies on the same whisker-based system used for larger prey, but the strikes require greater precision. An insect larva only a centimeter long presents a far smaller target than a 5-centimeter crab. The otter shrew must orient its jaws accurately based on whisker feedback alone, then snap closed on the tiny prey before it can dart into an inaccessible crevice. Mollusks, both snails and freshwater clams, are consumed when encountered, though crushing the shells requires repeated biting and sometimes banging the mollusk against rocks. The robust molars again prove their value here, applying focused pressure to crack the protective shells. Freshwater prawns and shrimp fall victim to the same hunting techniques used for crabs, though their smaller size and weaker defenses make them easier targets. The otter shrew can typically dispatch a prawn with a single well-placed bite, then consume it quickly without extensive processing. Mollusks, both snails and freshwater clams, are consumed when encountered, though crushing the shells requires repeated biting and sometimes banging the mollusk against rocks. The robust molars again prove their value here, applying focused pressure to crack the protective shells. Freshwater prawns and shrimp fall victim to the same hunting techniques used for crabs, though their smaller size and weaker defenses make them easier targets. The otter shrew can typically dispatch a prawn with a single well-placed bite, then consume it quickly without extensive processing. The preference for calm pools over fast-flowing riffles reflects both sensory and energetic considerations. In turbulent water, the chaotic flow patterns create noise in the whisker sensory system, making it harder to detect the subtle signatures of prey movement against the background of constant water turbulence. A fish swimming past in still water creates a distinctive pressure signature that the vibrissae can readily detect. The same fish passing through turbulent flow generates a signal lost in the confusion of eddies, waves, and chaotic currents. Additionally, maintaining position in strong current demands continuous swimming effort, burning calories that could otherwise go toward growth, reproduction, or fat storage. Calm pools and slow-flowing reaches offer stable hunting platforms where the otter shrew can patrol methodically while expending minimal energy on station keeping. Cover and refuge features play important roles in hunting habitat selection. While hunting, these animals remain vulnerable to their own predators, including larger fish, water snakes, monitor lizards, and various raptors that strike from above when otter shrews surface to breathe. Hunting locations that offer quick access to protective cover, whether submerged root masses, overhanging banks, or rock piles, allow otter shrews to forage while maintaining escape options. If danger threatens, the animal can dart into cover and wait for the threat to pass before resuming hunting. The regular and predictable nature of foraging routines suggests that otter shrews develop cognitive maps of their territories, learning which locations consistently yield prey and which prove less productive. An individual animal may visit the same sequence of pools repeatedly, timing its arrival at each location to coincide with periods of peak prey activity. This spatial memory and routine establishment represents cognitive sophistication beyond simple instinct, indicating that otter shrew brains are capable of complex spatial learning despite their modest absolute size. When particularly rich feeding opportunities arise, otter shrews may concentrate their efforts on a small area rather than ranging widely. A pool where crabs are molting and thus more vulnerable might hold an otter shrew's attention for an extended period. Similarly, if small fish congregate in a confined space, the otter shrew exploits this bonanza before the school disperses. This tactical flexibility, knowing when to work a productive patch intensively versus when to move on to fresh hunting grounds, maximizes foraging efficiency across variable prey distributions. The specialized carnivorous lifestyle of otter shrews sets them apart from their tenrec relatives, most of which consume a mixed diet of invertebrates and sometimes plant material. The commitment to pure carnivory reflects the abundant protein available in freshwater ecosystems, but also imposes constraints. Unlike herbivores that can spend hours grazing on stationary food, carnivores must repeatedly locate, pursue, and subdue prey items that actively avoid being eaten. Success depends entirely on the effectiveness of the whisker-based detection system and the learned hunting skills that individual otter shrews develop through experience. In the darkness of African forest streams, where vision-dependent predators would flounder helplessly, otter shrews hunt with precision and efficiency, their vibrissae extending their perception into the surrounding water like invisible fingers reaching out to grasp the movements of unseen prey. This specialized sensory world allows these small carnivores to thrive in an ecological niche that would otherwise go unexploited by mammalian predators. Chapter 5. Darkness and Territory. As afternoon shadows lengthen across the tropical rainforest streams of Central Africa, a profound transformation begins in the activity patterns of the resident otter shrews. Throughout the daylight hours, these small carnivores have remained hidden in their bankside burrows, while diurnal predators patrolled overhead. But as the sun drops below the canopy and darkness spreads across the forest floor, the otter shrews stir from their daytime refuges and prepare to enter the realm where they reign as specialized nocturnal hunters. The transition from day to night brings more than just reduced light levels to the forest stream ecosystem. The entire community of organisms shifts in composition as nocturnal species emerge and diurnal forms retreat to shelter. Water temperatures typically drop several degrees during the night. The soundscape changes as daytime bird calls give way to the chirping of crickets and the occasional distant calls of night birds. Into this transformed environment, the otter shrew emerges to claim its hunting grounds. The burrow from which an otter shrew begins its nightly activities represents far more than a simple hole in the bank. These structures show clear evidence of deliberate construction and maintenance, revealing that otter shrews invest considerable effort in creating secure resting sites. The burrow entrance can be positioned above or below the surface level of the stream, though underwater openings provide additional security from terrestrial predators and prevent most scent trails from reaching mammalian predators hunting by smell along the banks. From the entrance, a tunnel angles upward through the earth and roots of the stream bank. The tunnel rises above the high water mark, ensuring that even during flood events, an air-filled chamber remains accessible. This chamber forms the heart of the burrow system. Here the animal constructs its nest, gathering dry leaves and other plant materials that provide insulation and cushioning. The nest chamber must stay dry despite its proximity to water, protected by the rising tunnel configuration that prevents flooding under all but the most extreme high water events. What makes this burrow arrangement particularly noteworthy is that individual otter shrews do not maintain just one permanent residence. Instead, they frequently change burrows, moving between several different refuges distributed across their territory. This itinerant pattern may serve multiple functions. Parasites that accumulate in a frequently used burrow never build up to intolerable levels if the host regularly abandons the site for weeks at a time. Predators that learn the location of one burrow find it empty when they return. The mobility also allows the otter shrew to position itself optimally for efficient access to different areas, as conditions shift seasonally or as particular locations become temporarily less productive through intensive foraging. As darkness becomes complete, the otter shrew emerges for the night. The nightly activity pattern does not consist of one continuous hunting session from dusk until dawn. Rather, otter shrews structure their nights around several foraging bouts separated by rest periods. During these breaks between hunting, the otter shrew engages in grooming, systematically working through its fur to maintain the waterproof properties of the coat. The animal may also simply rest, conserving energy between foraging efforts. This rhythmic pattern of activity and rest continues throughout the night, though the intensity and duration of foraging bouts may vary with hunting success. The flexibility in this pattern suggests that otter shrews respond tactically to their immediate circumstances rather than following a rigid schedule. The total distance covered during a night's foraging varies by species and individual, but for giant otter shrews, movements of up to 800 meters along the stream have been documented. This represents substantial coverage of available habitat as the animal systematically works through the pools, riffles, and quiet backwaters within its territory. The route followed shows both regularity and variation, with certain productive locations receiving visits every night, though the sequence may change. The solitary nature of otter shrew life becomes evident when considering how individuals space themselves across suitable habitat. Unlike many mammal species that live in family groups, pairs, or larger social units, otter shrews lead essentially isolated existences. Adults tolerate each other's proximity only during the brief breeding season. Outside of breeding periods, otter shrews actively avoid one another, each individual maintaining exclusive access to a segment of stream or river. This solitary territorial system manifests most clearly in the spacing of individuals along watercourses. In high-quality habitat with abundant resources and optimal structural features, territories may be as short as 500 meters of stream length, with one adult occupying each such section. In poorer habitat, territories stretch longer, perhaps approaching a kilometer or more. The density variation means that the finest habitats can support higher concentrations of individuals, though several hundred meters typically separate neighboring territories. The mechanisms by which otter shrews establish and maintain these territories have only recently become clear through careful observation of their remarkable latrine behavior. Unlike many mammals that mark territories through scent glands, otter shrews employ a different strategy. They establish latrines, specific locations where feces are repeatedly deposited to create conspicuous piles that serve as individual territorial markers. These latrines are not placed randomly, but at strategic locations that convey maximum information to potential intruders. The mechanisms by which otter shrews establish and maintain these territories have only recently become clear through careful observation of their remarkable latrine behavior. Unlike many mammals that mark territories through scent glands, otter shrews employ a different strategy. They establish latrines, specific locations where feces are repeatedly deposited to create conspicuous piles that serve as individual territorial markers. These latrines are not placed randomly, but at strategic locations that convey maximum information to potential intruders. The characteristics of latrine sites show consistent patterns across different territories and different individual otter shrews. The sites are always sheltered, placed under overhanging rocks, beneath dense root masses, or in other locations protected from rain that would wash away the deposits and from floods that would disperse them downstream. The latrines always sit above the normal stream floodline, safe from regular fluctuations in water level that occur during tropical rainstorms. An established latrine accumulates substantial deposits over time as the resident otter shrew visits repeatedly. The site of such a latrine is unmistakable, a dark pile positioned prominently at a site any intruding otter shrew would likely encounter when moving through the territory. The scent from these latrines carries in the water and air, providing olfactory signals that complement the visual cue. The interpretation of latrine function as territorial markers rests on several lines of evidence. Latrines are regularly distributed along streams at intervals that correspond roughly to territory sizes. Residents visit their latrines with predictable regularity, maintaining fresh scent marks that signal continued occupancy. The prominent placement of latrines at sites any traveling otter shrew would encounter suggests they serve a communication function rather than simply convenient toilet locations. Latrines are probably used to mark territorial boundaries, allowing individuals to space themselves without direct confrontation. The territorial system maintained through latrine marking provides benefits that justify the costs of defending exclusive areas. By excluding competitors, a resident otter shrew ensures that resources within its territory are not depleted by other foragers. This allows the resident to learn the locations of productive sites and return to them reliably. The predictable resource supply within a defended territory likely exceeds what the animal could obtain through nomadic foraging in the face of competition from multiple individuals working the same waters. The costs of territoriality include the energy and time invested in patrolling boundaries and maintaining latrine markers, plus the potential for aggressive encounters if intruders do not respect the scent markers. While actual fighting between otter shrews has rarely been documented, the capacity for aggressive interaction is suggested by the sharp teeth and powerful bite these animals possess. The latrine marking system presumably functions to minimize the need for direct confrontation by clearly advertising territory boundaries. The habitat within which these territorial and activity patterns play out consists of the small to medium streams and rivers that drain the tropical rainforests of Central and Western Africa. These are not the mighty rivers that capture popular imagination, but rather their tributaries, watercourses typically a few meters wide, often less, flowing through dense forest where sunlight barely penetrates to the water surface even at midday. The water itself varies from nearly clear during dry periods to heavily laden with suspended sediments during and after rains. The physical structure of these streams creates the microhabitats that otter shrews require. Fallen logs spanning the channel create small waterfalls and pools. Exposed root masses from riverside trees extend into the water, creating three-dimensional structure. Rocks of various sizes accumulate in certain reaches. Undercut banks where the current has eroded soil from beneath the roots provide additional structural complexity. All these features combine to create heterogeneous habitat that supports the nocturnal hunting activities otter shrews depend upon. The tropical rainforest setting imposes its own rhythms on otter shrew life. Unlike temperate regions with pronounced seasons, the equatorial forests where most otter shrews live experience relatively constant temperatures year-round. Daylight remains close to 12 hours throughout the year, so the timing of sunset and dawn varies little with seasons. What does vary is rainfall, with distinct wet and dry seasons in many parts of the otter shrew range. During the wet season, stream flows increase. Some channels that were dry during the dry season now carry water, and resources become more dispersed across expanded aquatic habitat. During the dry season, streams contract, sometimes shrinking to a series of isolated pools connected by trickles. These seasonal changes influence otter shrew behavior and distribution. During high water in the wet season, some individuals may retreat from the main channels to exploit temporary pools in the forest, small water bodies created by accumulated rainfall. However, the otter shrew must return to permanent waters before the temporary pools dry. The dry season concentrates both resources and residents in the shrinking available water, which may intensify territorial conflicts if boundaries become unclear as water levels drop and the landscape transforms. As the night progresses toward dawn, the otter shrew's activity gradually winds down. The return to the burrow follows a fairly direct route. Upon reaching the burrow, the otter shrew pauses at the entrance for a final look around, then enters and disappears up the tunnel to its nest chamber. Inside the burrow, as dawn breaks outside, the otter shrew settles into the nest it constructed from dried leaves and plant fibers. The metabolism slows as the animal enters a resting state, though true hibernation never occurs in these tropical mammals that experience relatively constant temperatures. Throughout the day, the otter shrew remains essentially inactive until the approach of the next dusk signals the start of another cycle. This daily rhythm, repeated night after night, defines the temporal dimension of otter shrew existence. The spatial dimension finds expression in the territory they defend through their latrine marking system, the several hundred meters of stream they know intimately and exploit exclusively. Together, the nocturnal piming and territorial spacing create a social system of solitary individuals active at night, each one a master of its particular stretch of rainforest river, rarely, if ever, encountering others of their kind outside of the breeding season. This organization allows multiple otter shrews to coexist in productive habitat without direct competition, dividing the available resources through a territorial framework maintained by scent and learned recognition of boundaries. This organization allows multiple otter shrews to coexist in productive habitat without direct competition, dividing the available resources through a territorial framework maintained by scent and learned recognition of boundaries. Chapter 6. Conservation threats from habitat destruction, deforestation, and mining operations causing population decline. The streams that wind through the tropical rainforests of Central and Western Africa appear timeless, as if they have flowed unchanged through these forests since the age of dinosaurs. The otter shrews hunting in their dark waters seem equally permanent, the culmination of 50 million years of evolutionary refinement perfectly adapted to an ecological niche that appears stable and secure. Yet this appearance of permanence is profoundly deceptive. Across the ranges of all three otter shrew species, a constellation of human activities is systematically dismantling the habitat upon which these ancient mammals depend, threatening to erase in mere decades what evolution spent epochs creating. The most pervasive threat comes not from any single catastrophic event, but from the steady, relentless conversion of tropical rainforest to other land uses. Deforestation in Central Africa proceeds through multiple mechanisms, each contributing to the fragmentation and degradation of otter shrew habitat. Subsistence farmers clear forest patches to plant crops, creating a patchwork of agricultural fields interspersed with forest remnants. Commercial logging operations extract valuable timber species, opening the canopy and altering the microclimate of the forest floor. The establishment of palm oil plantations, an increasingly common land use across tropical regions, replaces diverse forest ecosystems with monoculture plantations that support only a fraction of the original biodiversity. Each of these activities transforms not just the terrestrial environment, but the aquatic systems that flow through the landscape. When forest cover is removed from a watershed, the hydrological regime of streams changes dramatically. Rainfall that once intercepted by the forest canopy and gradually released through the soil into streams now runs directly off bare ground, creating flash floods during storms and reduced dry season flows when the rains cease. The loss of tree roots that once stabilized stream banks leads to increased erosion. Soil that should remain in place on hillsides instead washes into waterways with every heavy rain. This erosion creates conditions fundamentally hostile to otter shrews. The streams that once ran clear or only mildly turbid during the dry season now carry heavy sediment loads year-round. The fine particles of suspended clay and silt scatter what little light penetrates the forest canopy, reducing visibility to nothing even in shallow water. While otter shrews do not rely primarily on vision for hunting, the excessive sedimentation affects their prey populations. Many aquatic insects require clean gravel or sand substrates for their larvae. Freshwater crabs need rocky crevices and stable banks for shelter. Fish that once bred in clean gravels find their spawning grounds smothered under layers of fine sediment. As these prey populations decline, the carrying capacity of streams for otter shrews drops correspondingly. The problem intensifies in regions like Cameroon, where deforestation has reached particularly severe levels. Studies documenting otter shroom distribution note that these animals avoid streams degraded by erosion resulting from upstream forest loss. The behavioral data suggests that otter shrews can tolerate seasonally turbid conditions, the natural muddiness that occurs during rainstorms in even pristine watersheds. But streams that remain permanently clouded from chronic erosion see otter shrews abandon the habitat entirely or fail to colonize stretches that might otherwise appear suitable. The animals simply cannot persist where their prey base has collapsed due to poor water quality. Beyond the indirect effects of sedimentation, deforestation fragments the continuous riparian corridors that otter shrews require for maintaining viable populations. These animals are not strong overland travelers. Their short legs and heavy bodies, so well adapted to aquatic life, make terrestrial movement difficult and energetically costly. When forest clearing creates gaps in the riparian vegetation, stretches of open ground separate patches of suitable habitat. An otter shrew faces daunting challenges trying to disperse from its natal territory to establish a new one if the route requires crossing cleared agricultural land under the full sun, exposed to aerial predators, and without the cover of streamside vegetation. This fragmentation effect manifests most severely in the case of the Nimba otter shrew, the species facing the most acute conservation crisis within the family. This smallest member of the otter shrew family occupies a range confined to the highlands surrounding Mount Nimba, a mountain that straddles the borders of Guinea, Liberia, and the Ivory Coast. The total area inhabited by this species measures less than 5,000 square kilometers, a range already restrictive compared to the broad distribution of the giant otter shrew across Central Africa. Within this limited range, the available habitat has become increasingly fragmented through a combination of agricultural expansion and, most devastatingly, industrial mining operations. Mount Nimba harbors some of the richest iron ore deposits in West Africa. The mountain's geological history created concentrations of high-grade iron ore that mining companies have exploited for decades and continue to covet for future extraction. The existing mining operations have already consumed substantial areas of otter shrew habitat, physically removing entire hillsides and stream valleys as earth-moving equipment strips away the overburden to access the ore beneath. But the damage extends far beyond the immediate footprint of the mines themselves. Mining operations generate enormous quantities of waste rock and tailings that must be disposed of somewhere. These materials often end up in valleys where they bury streams or create artificial barriers that fragment aquatic habitat. The processing of ore requires water, which is drawn from local streams and rivers, reducing flow rates in waterways downstream of the extraction points. Most insidiously, the mining process generates toxic runoff laden with heavy metals and processing chemicals. This contaminated water flows into the stream systems that drain Mount Nimba, carrying its poison to exactly the habitats where Nimba otter shrews hunt for crabs and aquatic insects. The streams that receive this mining effluent experience dramatic changes in water chemistry. Heavy metals, including iron, manganese, and potentially mercury, depending on the extraction methods, accumulate in the sediments and bioaccumulate in the tissues of aquatic organisms. The prey species that Nimba otter shrews depend upon either die directly from acute toxicity or accumulate sublethal contamination that passes up the food chain when an otter shrew consumes a contaminated crab or fish. Over time, the otter shrew itself accumulates these toxins, potentially suffering reproductive impairment, immune system damage, or premature death. Even beyond the areas directly affected by mining, the Nimba otter shrew faces habitat loss from wetland rice agriculture practiced by local communities. The cultivation of rice in small valley-bottom wetlands requires modification of the natural hydrology, the construction of paddy buns, and water control structures that alter stream flow patterns and create barriers to otter shrew movement. While small-scale traditional agriculture may have coexisted with otter shrew populations for generations, the increasing intensity and spatial extent of cultivation progressively reduces available habitat. Each valley converted to rice production represents one less stream system available for otter shrews. The population consequences of these combined threats have been documented with alarming clarity. Surveys attempting to estimate Nimba otter shrew numbers suggest a total wild population of perhaps 2,500 to 3,500 individuals, though substantial uncertainty surrounds these estimates given the difficulty of detecting these nocturnal, aquatic, and secretive animals. More concerning than the absolute numbers is the trajectory. Population monitoring indicates a decline rate of approximately 1 individual per 10 square kilometers per year. Across the species' limited range, this translates to a loss of nearly 500 otter shrews annually. If this decline rate continued unchecked, mathematical projections suggested the Nimba otter shrew would reach functional extinction, the point where too few individuals remain to sustain reproduction, sometime between 2017 and 2020. The species has survived past this predicted extinction window, indicating either that the population estimates were too pessimistic, that conservation efforts have had some effect, or that the species has found refuges where decline rates are lower than the range-wide average. Nevertheless, the trajectory remains deeply concerning. A species confined to a tiny range, experiencing ongoing habitat loss and fragmentation, with no signs that the underlying threats are being adequately addressed. Attempts to establish captive populations that might serve as insurance against extinction in the wild have proven frustratingly unsuccessful. The few times Nimba otter shrews have been brought into captivity, they have not only failed to breed, but have rapidly declined in health and died within days. The closely related giant otter shrew shows similarly poor survival in captivity, with documented cases of captive individuals surviving as little as 1 day and rarely more than 2 weeks. The reasons for this catastrophic failure to thrive in captivity remain unclear. Perhaps the stress of confinement proves overwhelming for animals adapted to ranging widely through complex aquatic habitats. Perhaps their specialized dietary requirements cannot be adequately replicated with food sources available to zoos and research facilities. Perhaps they carry pathogens that remain benign in wild conditions but become lethal when the animals experience the physiological stress of captivity. Whatever the cause, the inability to maintain otter shrews in captivity means that conservation must focus entirely on protecting wild populations and their habitats. There is no fallback option of captive breeding programs that have saved other endangered species from extinction. If wild populations collapse, these species will simply vanish, carrying with them their unique evolutionary heritage and ecological roles. The Ruwenzori otter shrew, while not facing quite as severe a crisis as its Nimba relative, experiences its own set of conservation challenges. This species inhabits the mountain streams of the Albertine Rift, a region encompassing parts of Uganda, Rwanda, and the Democratic Republic of Congo. Political instability and armed conflict in parts of this region have made conservation work difficult and sometimes dangerous. Forests are cleared for agricultural expansion by growing human populations. Streams are degraded by erosion and pollution. The species' relatively restricted range along the mountains of the eastern Congo makes it vulnerable to localized threats. Conservation assessments classify it as near threatened, a designation indicating that while not immediately facing extinction, the trajectory points toward endangerment if current trends continue. Even the giant otter shrew, with its broad distribution across the Congo Basin and adjacent regions, faces a declining population despite its current classification as least concern. The very breadth of its range exposes it to threats across a vast geographic area. Deforestation proceeds across Central Africa, fragmenting once continuous forest cover into isolated patches. Logging roads open previously inaccessible forest to human settlement and resource extraction. The bushmeat trade, while not targeting otter shrews as primary quarry, occasionally results in their capture. More significantly, the giant otter shrew's dense, water-repellent fur has commercial value. Hunting for pelts, while not conducted at industrial scales, represents a persistent source of mortality that compounds other threats. Incidental mortality from fishing activities adds another incremental drain on populations. Local communities fish the same streams and rivers that otter shrews hunt in, employing techniques ranging from simple hook and line to woven fish traps and nets. An otter shrew investigating a fish trap or swimming into a net becomes entangled and drowns before it can free itself. Each such incident removes an individual from the breeding population. Multiply this by thousands of fishing sites across the species range, and the cumulative impact becomes significant, even though any single fisherman might encounter an otter shrew in their gear only once or twice in a lifetime. The conservation challenge is compounded by the basic lack of information about otter shrew biology and ecology. Compared to charismatic megafauna like elephants or gorillas that attract substantial research attention and conservation funding, otter shrews remain poorly studied. Their nocturnal habits make observation difficult. Their aquatic lifestyle means they cannot be easily studied using the camera traps that have revolutionized research on terrestrial mammals. Their secretive behavior and low densities mean that even dedicated field researchers may spend weeks in otter shrew habitat without encountering these animals. This knowledge gap hampers conservation planning. Without understanding their population sizes, reproductive rates, dispersal capabilities, and specific habitat requirements, conservationists struggle to design effective protection strategies. The few protected areas that encompass otter shrew habitat provide some hope but also illustrate the challenges of effective conservation. The Mount Nimba Strict Nature Reserve was established to protect the unique biodiversity of this mountain and includes within its boundaries prime Nimba otter shrew habitat. Yet the reserve sits immediately adjacent to active mining operations. The boundaries drawn on maps provide no protection against toxic runoff that flows downstream from mining areas outside the reserve. Enforcement of protections against poaching remains inconsistent. The reserve essentially functions as a habitat island surrounded by human-dominated landscapes, and the otter shrew population within it faces all the vulnerabilities of small, isolated populations, genetic bottlenecks, demographic stochasticity, and limited ability to recolonize if local extinctions occur. More encouraging signs emerged from surveys conducted in Liberia's East Nimba Nature Reserve in 2013, which found apparently healthy populations of Nimba otter shrews within that protected area. This suggests that where habitat protection is effective and threats are minimized, these animals can persist. The challenge lies in expanding such protection across a sufficient proportion of the species ranges to ensure long-term viability. The evolutionary perspective adds profound urgency to otter shrew conservation. These three species represent the sole surviving members of an ancient family that diverged from Malagasy tenrex nearly 50 million years ago. Every otter shrew carries in its genome the accumulated genetic heritage of that vast span of evolutionary time. The morphological adaptations, the specialized behaviors, the unique position in tropical stream ecosystems, all of this represents biological information that took millions of years to evolve through natural selection. The extinction of any otter shrew species would erase that information irrevocably, impoverishing the planet's biological heritage in ways that cannot be reversed or compensated through any human effort. Consider what would be lost if the Nimba otter shrew vanishes. This species represents one of only 3 surviving branches of the family Potamogalidae. Its loss would reduce by 1/3 the evolutionary diversity within this ancient lineage. The specific adaptations it evolved for life in mountain streams, subtle differences in morphology and behavior that distinguish it from its relatives, would disappear. The ecological role it plays in mountain stream ecosystems, influencing prey populations and nutrient cycling through its predation, would remain unfilled by any other species. The genetic diversity within the species, shaped by the particular selection pressures of the Mount Nimba region, would be eliminated. Multiply this loss by 3 if all otter shrew species go extinct, and the magnitude of what is at stake becomes clear. An entire family of mammals, representing one of the few surviving lineages of ancient African insectivores, would vanish. Future generations would know otter shrews only through museum specimens and scientific descriptions, unable to witness these remarkable animals undulating through forest streams or hear the splash as they surface in the tropical night. The path forward for otter shrew conservation requires addressing the root causes of habitat degradation while protecting the remaining strongholds where populations persist. This means regulating mining operations to minimize environmental damage and prevent toxic runoff from reaching streams. It means establishing and enforcing larger protected areas with buffers around core habitat. It means working with local communities to develop sustainable practices for agriculture and fishing that can coexist with otter shrew populations. It means continuing research to fill the knowledge gaps that hamper conservation planning. Most fundamentally, it means recognizing that the streams of tropical Africa harbor treasures worthy of protection, small, obscure mammals that nonetheless represent irreplaceable products of evolution's creative power. The otter shrews of Africa represent a remarkable evolutionary achievement, a 50-million-year journey from shared ancestors with Malagasy kenrex to specialized aquatic hunters using crocodilian swimming mechanics and whisker-based sensory systems. These 3 species, each adapted to forest stream habitats, embody nature's capacity for innovation across deep time. Yet this ancient lineage now faces existential threats from deforestation, mining, and habitat fragmentation, with the Nimba otter shrew approaching extinction. Their decline reflects a broader crisis facing specialized species with restricted ranges and specific habitat requirements. When an entire mammalian family, representing millions of years of evolutionary refinement, can disappear within a human lifetime due to preventable habitat destruction, we must question what other irreplaceable biological treasures we are losing before we even understand them. Thank you for listening to this exploration of one of Africa's most ancient and endangered mammalian lineages.